Well, good morning, good evening, good afternoon, wherever you are in the time zone. Welcome to this webinar. Myself and Oscar and Moz here are going to take you through some ideas and concepts based on the new wave of semiconductors for the use to improve trust, AI, and information overload, issues which are paramount and close to our hearts. Before I tell you a little bit about Mobica Cognizant, I'm going to hand over to Moz and Oscar and let them introduce themselves. I am the VP of Semiconductor at Cognizant Mobica, which essentially means that I look after the clients in the semiconductor area. I'll hand over to Moz and let him talk a little bit about himself first.
Yeah, sure. So my name is Moz Ahmed. I work in the silicon sector here at Mobica. I've been in the industry for 23 years, at Mobica for 12 years. And in that time, I've worked across a number of different vertical sectors, but mainly focused on silicon, our silicon customers.
And Oscar?
Yeah, so I am serving as a technical solutions architect at the technology office. I've been a part of Mobica team for over 10 years now. So my main areas of interest are Linux kernel and firmware development and GPU related topics, especially Vulkan and drivers for it and general architecture of hardware accelerators. Yeah, that's all.
Thanks both. Well, as you can see, we've got two very experienced engineers here who've worked very much at on the sorts of solutions and problems that Mobica typically gets brought in to solve. So let me tell you a little bit about Mobica and our parent company now, Cognizant. We have about 800 engineers. We've got offices across Poland where we do most of our work, but we also, we were formed in Manchester in England, where the computer was invented, frankly. With at least the first commercial commuter, the Manchester Baby and the Franti Mark 1. And, we've been acquired last year by Cognizant, and that brings us now to sort of 7,000 engineers at 2,000 technical specialists. And we've become part of their Internet of Things group. And the reason that we've become part of that organization is because Mobica very much focuses on the glue, where the software and the hardware meet, the firmware. So we've done a lot of work in that area in terms of in-home technologies, industrial automation, cars, software devices, and wearables. And in the last 10 years, we kind of noticed the move from, the last 10 years was focused on cloud native, and then we think the next 10 years will be focused on edge native. So we're interested in talking about why that move to the edge will happen and how you should engage with it. Do you want to pick up the first slide there, Moz?
Yep.
Okay, so here's a slide of our the way we see the market, the value chain for semiconductors. So you look at the market demand there at the left-hand side. What you see is these various things that are driving the analysis of semiconductor manufacturers or IP creators. So people who create the architectures, the new designs for semiconductors. I'll let you, Moz will speak later about the industry segments. But to deal with the first one's called security. So whilst theoretically security has been something that's been understood for about 50 years, frankly, with the RSA algorithm, etc., it hasn't really been implementable right down to the hardware. And so what we've now seen is that these features come into the hardware at all levels. So whether that be highly performant hardware in data centers or hardware right at the edge. And by right at the edge, I mean, in the locks on your cars, on your house, in your homes. So security is one of the things that's being engineered into new semiconductor features. The second area, which is fairly niche, but I'm mentioning it because something that Mobica specializes in, is an area of functional safety. And what functional safety is, it's to some degree wrapped up security, because you need to know that your solution, your technology in place is secure, and it's not being attacked or down by anybody else. And so that when when you deliver a product such as a generation plant or a plane or a car, you're delivering something that causes loss of life, possibly catastrophic loss of life. And so we work with semiconductor manufacturers and the people who provide the system software to deliver drivers and pieces of firmware and software which are functionally safe. And what that means is that it's software that it performs what it's meant to do when it's meant to do it. So, whether that's, doesn't matter what element that is in the software stack, whether that's the hardware, the real-time operating system, or the driver, if you ask it to do the job it's going to do it within the time it's meant to do it, at the time it's meant to do it, and it's not going to fail. And there are a lot of, there's a lot of engineering that goes into that. In particular, you need to make sure that the languages and the software that you use to build that technology conform to the standards and operate safely. And the actual international standard for that is ISO 26262. So the next area which is driving the new features in the hardware is high performance and hardware acceleration. There's a lot of new players in the high performance area, and there are lots of different types of architectures come into play over the last 5 or 10 years. And you can look at companies like Mythic, GraphCore, Sambanova, Grok, Rebellions, and then the hyperscalers themselves, which are the Alibabas and the Googles and the Microsofts of this world, and the Amazons, AWS. They've been developing their own accelerators and semiconductors as well. And what you're seeing there is, these accelerators being put into place, which kind of a little bit return to times of old. Whereas historically we focused on a general purpose computer, now you've got these accelerators, which are small compute engines, often usually guided by the CPU, which deal with jobs which are essentially a kind of one-task job, such as compression and encryption. So that's high performance hardware acceleration. Third area is graphics and games. In financial systems, there's something called high intensity trading, and that's where you run transactions in milliseconds or even microseconds to generate a small margin of profit on a large sum of money. And in gaming, latency, or in fact any real-time system, latency is really important as well. You need to have things respond and do what you need them to do when you need to do them. So that's one area in which high performance hardware and the software that sits above it needs to be engineered. The other one is, areas such as more demand for realism in computer graphics, or in the ability of what the GPU can to do support features like ray tracing, which is something that deals with points of light in a picture, which create shadows and create reflections. And the ray tracing hardware allows you to deal with that more realistically in a more performant way. And the final one, which is edge native and embedded, this is where, again, dealing with ultra latency needs, the new hardware comes along, and it's used in solutions such as time stock management, pricing in the shops at real time, safety in construction. So if I were to walk onto a site, to be recognized as being somebody who's not dressed safely, doesn't have a hard hat on, maybe doing something unsafe, and to be able to conduct interventions, as before incidents happen. Other examples might be traffic flow management for event management in emergency situations. So these are the areas of application where there's market demand. And if I was working for a semiconductor manufacturer, or indeed anybody involved in that value chain, I'd be looking at providing technologies and solutions which deliver those outcomes in the best possible way. And so that's what's driving demand.
Shall I jump in there?
Yeah, just
So our concept, or our understanding of the value chain kind of describes how industry has responded to these demands for silicon. So obviously that is not just a response, they've also kind of created the market for some of these applications. But originally you'd have vertically integrated silicon vendors, And so I've kind of jumped to the third category there to begin with. And so these are your classical companies that design it, produce it, and sell silicon and solutions around it. And so you have your companies like Texas Instruments, NXP, ST Micro, and IBM to some extent, although they have also they do offer other services to other players in the market. And so that's what a typical semiconductor company used to look like. And then you had other companies that came along and decided to sell designs for a living. And so you have like companies like ARM that sell IP that's integrated into the silicon. Imagination Technologies, Synopsys, these all design parts of chips, and these are integrated by chip manufacturers into their products. Fabless semiconductor companies actually create the designs but don't sell them. They manufacture or they contract out the manufacture of their own chips. So Apple do that with their M1, M2, and M3 silicon. Qualcomm, NVIDIA don't have their own foundries. And so they contract out to companies like TSMC, Global Foundries, and others to produce chips. Famously, AMD split and split into AMD now, which is fabless, and they contract out the manufacture of their chips to Global Foundries that used to be a part of their company. So these are the kind of partner organizations that we seek to work with in this sector.
Yeah, actually, Moz, I might add a bit more to that, because I was thinking about the microarchitecture, the design of the processor areas, and when you go back into the day, if we talk about desktop and data center as things move from big I and IBM stuff down to the silicon semiconductor solutions, it basically kind of coalesced around the Intel architecture once the likes of Sun and PA RISC and PowerPC had lost the race to be the most cost-effective provider of CPU cycles. And then the introduction of these IP licensors and creators, such as ARM, has made a massive difference, because a lot of those other companies down there, such as MXT and ST, and indeed NVIDIA, they license that for the CPU, and then they put in their accelerators and their high performance elements around that. And that's, that fluidity and that speed within the market now has really led to this new wave of technology coming through. I don't know. And anyway, Oscar, I think we're going to hand over to you next to talk a little bit about third area of this diagram.
It's just worth to know to this, referring to the slide we currently see. So there is one more aspect worth covering. It's software ecosystem. So for the last couple of years, we could see that the many companies invested a lot in ecosystem, including open source software, for a reason, because we can produce a hardware, but we need the producers to adapt to it. So we want the market to adapt this hardware solutions, and for this we need transparent, clear APIs and also easy deployable system. So that's why we saw many silicon companies investing a lot in open source software for the adaptation in the common framework used in the cloud, for example, in the HTTP server, for them to be used as accelerators. And also, it's quite important to have a good packaging and deployment system for the developers to easily deploy solutions provided by hardware vendors. Yeah, and that's all from my side.
I guess just to add to that, sorry, Robert. I'd say it's not necessarily just open source. I'd say like companies like NVIDIA really leverage their software ecosystem to tie people into their onto their platform. So they're making hay by selling NVIDIA accelerators, but they've locked people into using those accelerators by making or being the first movers on frameworks like CUDA to tie people onto their hardware. So I guess what the wider part of the software ecosystem is that it's a value add. It's a way to facilitate silicon or semiconductor vendors for them to facilitate the integration of their chips into products and devices.
NVIDIA was quite exception here. I mean, just they are the leaders, and they could create their own ecosystems. For other smaller producers, they had to convince the community and even private companies to use their software, to use their hardware through easy adaptation to the software. So there are different depending on how big you are and how cutting edge technology you produce.
Yeah, whether you're a first mover or not.
Yeah, it'll be interesting to see with NVIDIA whether they become the last example of somebody who drives a real big movement in their direction by the use of a proprietary technology. I mean, for me, I come from a sort of previous generation to you two guys, but I remember the guys who did it really successfully back in the day with Microsoft. So the Microsoft, Intel, IBM triumvirate kind of went on to dominate the world for a while. And one of the ways they did it was the tools that are available and the sophistication of those tools and the ease of use of those tools for the platform, for the developer, were far superior. So I'm talking about the late 80s, early 90s, far superior to anything you could find in the Unix world. And I mean, that's changed now. So Oscar, there you mentioned the free open source thing. There's a whole heap of sophisticated tools out there. And one of example I'll give you later on. There's a whole heap of sophisticated tools out there, and a lot of them are being developed by companies like Mobica on behalf of people who want to promote, make sure their semiconductor technology is used out in the marketplace. But they're not software specialists themselves. They're focusing on getting their product out, which is either the device or the chip itself or the board that the chip sits on. So yeah, there's a lot going on. There is this massive new wave coming forward. So it's an interesting time for sure.
Shall we move on to the next slide?
Sure.
Okay, so this is we're talking about security, trust zones, and AI, and these are what we feel are trends and market forces that are going to be drivers for the sale of silicon and also the ecosystems around them, as we've described. So, firstly, the security aspect. Given the proliferation of devices that are connected, the current estimates are that there's 15 billion devices connected today, and that figure is likely to double by the end of the decade. So given this wide and large attack surface, legislators are obviously concerned and are looking to regulate the market to ensure that the risk of hacks to these devices that are all interconnected are mitigated. So whether they're consumer devices or whether they're critical pieces of infrastructure, they need to be secure to various levels. So similar legislations in the works in the EU and in the US. In the EU, it's called the Cybersecurity Resilience Act. And there'll be stiff penalties and a framework for making sure that manufacturers and vendors maintain good security in their devices. So the consequences of these requirements are that features will be required on the chips to properly secure devices. So this will drive demand for newer chips with secure elements integrated. So these secure elements include things like hardware-based encryption acceleration, physical unclonable functions. So hardware-based encryption increases speed of encryption, so you can have more complex algorithms with that perform within lower power envelopes. Physical and clonable functions allow the deployment of devices and the provisioning of those devices in a secure way. So they can be manufactured and installed with minimal involvement by technical personnel. Secure boot will allow, does allow secure update and anti-tamper mechanisms for devices. And then you have trusted execution environments that isolate execution of sensitive code and prevent it being tampered or monitored. So these are all kind of hardware elements that will need to be integrated into devices. Trust zones. Historically, these are, the security paradigm in place has been what's called a citadel model. So if you imagine a citadel with ramparts manned, a boat, secure battlements, all providing like a secure, almost impenetrable perimeter. The critical flaw with that security model is that once someone gets past the perimeter, the soft underbelly is exposed, and bad actors can run rampant and take whatever it is that you're protecting in the citadel. So the parallels with devices and software and hardware systems are obvious, but the consequence is that there's been a move to what's called a zero trust approach to dealing with these flaws. A zero trust approach requires that each subsystem within a architecture demands credentials or verification before allowing access, whether these are within the device itself or applications or services running on a platform, or devices interacting with each other in a network, such as the home, an office, a vehicle, or a smart city zone. So this segmentation of systems will add to the constantly evolving demands made of hardware to drive innovation of features to allow segmentation via things like virtualization, containerization, in increasingly smaller and smaller devices. So those are features that can be enabled via techniques in the silicon, but also an increase in computational capacity, whether that's storage, RAM, or compute power. So the third aspect that we think is going to drive demand is AI. Everyone's gone la-la for AI over the past few months, given the popularity of the generative AI. The computational demands being made of hardware systems is off the charts. Neural networks require massively parallel processing that's often accelerated by GPUs being retasked. Instead of calculating vertices to push pixels, they can do massively parallel computations required for neural networks. But better than these general purpose, so these are better than general purpose CPUs, but better still are dedicated neural processor designs that can provide better performance at low power budgets. And these will be integrated onto SoCs or as separate processor elements and systems to support inference at the edge of networks. So rather than pushing vast amounts of data back to data centers to be processed in the cloud, we'll see a trend to incorporate inferencing and processing at the network edge to speed up or reduce latency and reduce the amount of data that needs to be sent over the networks. Yeah, that's where we think some of the drivers will be.
They're all really good. No, don't move on to the next one yet, because they're all really good points, Moz. And Greg Lavender, the CTO at Intel, likes to go on with a little catchphrase. We're gonna everything the data, your data and your intellectual property is now going to be protected at rest, which it was done for ages when disks and in their various forms were encrypted. But in flight, which has also been done for ages with TLS and various encryptions, which encrypt the packets as they travel in the network, and at work. So as it's being used in the CPU with these new trust execution zones, that means that you're protected all the way through, and you're getting to the point whereby now, as I say, theoretically it's been there for ages, but where now you're able to be able to put your compute on the cloud or at the edge and know that, and have it attested that nobody else has interfered with it and seen it or used it, which is critical, for this move from cloud native to edge native to happen. So yeah, great points.
Yeah, I'm just also wondering about, will be there any universal solution for managing security for such IoT edge devices? I mean, currently the cloud providers are good at securing our data. But I am just wondering about the possibility of such mature products for IoT and the edge native devices, so our data could be handled securely.
Well, I mean, I think it will be in the hardware and the the real-time operating system and those things themselves. They will be. The architectures in there will make it secure. If I go back to the last millennium, when I was at university, a professor, we did a study on security, and at that time, the book that was used on security was called the Department of Defense, the US book, the Orange Book, and they had various levels of security. And I remember the comment was that the most secure one was a computer. The most secure computer was a computer which had no I/O connected to it and wasn't networked. I mean, it was completely useless, but you couldn't hack it, right? So we obviously got to the point now where we've got the technology to move away from that to something which is eminently accessible by those people who have the privilege to access it, and not at all accessible by anybody else. Obviously, as long as it's implemented properly, which is a big story in itself. But if theoretically the algorithms, the understandings there to make that true, I think at every level, it's just a question of getting the right engineering folks in place to ensure that it's implemented correctly, and then constantly testing it and validating that those attack services on there.
My opinion is that of course the hardware security and the everything that's related to the hardware will be handled by the hardware vendors or by the operating system. However, the high layers of services and application and its security will be handled by cloud and its providers. It's an opinion, not a fact. We'll see.
Yeah, I'd say what's driven standardization for the cloud is the desire to provide services for other people on your platform. And I think when it comes to embedded systems, they're not necessarily, well, I mean, that might change, but they're not necessarily an execution platform for other people's code. And so that's why I think maybe standardization might not work unless maybe it's the developers that might drive it to make their lives easier. I don't know.
I will cover this on my part.
All right. Okay, cool.
Partially, I will try to answer your question. Yeah.
Cool. All right, let's move on.
Yeah.
All right, so this is me, information overload. Yeah, so I certainly suffer from this. I suffer in the middle. I want to be in transmission. I want to be productive. I want to get stuff out, but constantly and receiving information from every device known to man. There's the iPad, there's the phone, there's the laptop. There's and they're all connected to other systems that are providing me with stacks and stacks of information. So I'm not alone in this. If you look at anybody, just take it in the office environment, just see what the diversity that's gone on. We've got documents and file types and stores of all shapes and sizes. Whether it be the Apple drives, your phone communicating with you, your G Drive, OneDrive, your different types of mail clients, all the messaging applications, whether it be Slack, WhatsApp, Facebook Messenger, Apple FaceTime, all these things. And then there's the social media providing with information, the Snapchats, the Facebooks, the Instagrams, more and more TikTok, YouTube is kind of a favorite of mine. And then there's still the mainstream media. So you're getting information from everywhere. You're kind of logging it. But you actually want some assistant to help you find that. And actually, Microsoft have done a pretty good job with their use of the term Copilot. Whether it'll be that useful, I don't know. But it's a pretty good concept of a Copilot. Certainly beats Clippy, if anyone remembers that. It's a pretty good concept. And it kind of does do what I think AI can help with. You know, it kind of says, I'm going to assist you understand and bring the information together. There's a long way to go. I mean, I looked at a seminar at MWC where representatives from Dell and Intel talked about, you know, you've been away on holiday, you get back, and all the information that you've received is being sifted, sorted, prioritized, and given, you know, you've been given hints on the actions to take. I suspect we're at least 5 years away from those sorts of applications being available, even though the core LLM and AI technology is there to help you do that. It's just a long way off, you know. I mean, the example I like to use, there's a lot before ChatGPT and the LLMs came off. A lot of people were talking about chatbots, and you know, and the end of the call center and things like that. Other than tell me how to reset my password, I've kind of yet to see a chatbot that answers any question that I seriously want to put to one of my service providers. In fact, I'll kind of go further than that. I wanted for, I have a network here that's provided by, I actually won't mention the name of the supplier, but I wanted to extend it. And I discovered, I wasn't told, but I discovered that my package entitled me to a whole bunch of extenders. And so I started to apply for these extenders, and you know, I had to communicate with the provider through a chatbot. And after a while, eventually somebody came on and said, oh yeah, we can send you one. I said, well, I'm entitled to 3, and I want to position throughout my property so that I have better network coverage, or at least better bandwidth for network coverage. And they said, yeah, well, we can send you one at a time. But this process of getting them, ordering one, then ordering the next one, then ordering the next one, took several weeks. And every time I went to that chatbot, I had to tell it who I was, what I was asking for. You know, it didn't have the proper context window. The technology implementation wasn't really there. And so, to be honest, much of the hype that goes on today is somewhat fantasy world. If you're thinking that I'm going to arrive back from holiday and everything's going to be organized and prioritized and maybe even actioned for me. So let me just give you a few more examples of that. Just this weekend, I'm a bit of a fan of YouTube. To be honest, I learn a lot from YouTube, and I think I'm discerning enough to know when I'm being told fibs or not. But one of the guys I like listening to is a guy called Fireship, and he does very short clips. There's a fashion for doing 2-hour YouTube video sessions, which are fine, but typically I don't have the time. And he looked at this, the idea that AI is going to put everybody out of a job. It's just not going to happen probably ever. Certainly not going to happen anytime soon. So let me go through the example that was given, because there is an area where it is providing this assistance and helping you with information overload, and one of them is in the area of software engineering. So there's a product from Cognition AI Labs called Devin that's come out, and what it does is it sort of mimics what a software engineer would do. You know, they'd find a snippet of information, they'd use that as a template for a piece of code, they'd probably figure out how that works to solve their requirement. They have their own experience. They run it through through a code editor. You compile it, you test it. Doesn't work, it breaks in certain areas. You go out and search again. And so these guys with Devin have created a new product similar to AutoGPT, but they decided to test it with a kind of more realistic software engineering benchmark called SWE. And that benchmark is an evaluation framework for how well the tool is doing. It's obviously a large language model behind it, how well that tells what that tool is doing. And it kind of looks at, you know, it looks through 2,294 pull request types in the software engineering platform, within the program repositories, on GitHub. So this is the open source development environment, which has become prevalent. You know, Linux Torvalds and the Linux Foundation movement created Git, and then it's positioned into 2 applications for developers to use, one called GitHub and one called GitLab. And so this is kind of part of the software development pipeline that a software engineer would use. So it then pulls those requests across, and it looks for those issues that are in there, and it runs through the problem of resolving those issues. And then you can figure out how well it does it. So within that table, they published up a bunch of data. And so I'll just run through the tools and show you what percentage of those issues, those 2024 issues, were resolved properly to respond to the pull request. So Claude 2, very popular LLM, solved 4.8%. Llama 13B, 3.97%. Llama 7B, 3%. ChatGPT 4, 1.74%. ChatGPT 3.5, 0.52%. So not really in a position where, like Rory Stewart said on The Rest Is Politics on March the 7th, that it's going to make 95% require 95% less coding, and therefore by implication you'd only need 5% of the engineers to produce the software that you're producing now. Not likely to happen, but Devin, because it's getting more realistic, it has produced a step change. So it's actually delivered close to 14%, 13.85% issue resolution, to be precise. So that is an example within an area which is a sort of, it's a proper problem-solving engineering area. It's an area which can be, defined and constrained. It's not one of these where you're kind of inferring things based on hunches or things like that. It's a proper engineering deterministic problem, and it has produced a step change of a significant step change if you're up to 13.85% in proper problem areas. And the same is happening within machine to machine. So what we're seeing is that these tools optimizing, solving problems. If I'm a network administrator, or if I work in telcos delivering telco high capacity communications networks, I need to make sure that those are maintained and available constantly, to the 6 nines and even better. And I want to maximize the capacity. I want to optimize that capacity. And the machine learning tools in that, again, are able to deal with a fairly constrained typical problem, which is a problem of networks and flow through networks and congestion on networks. And applying these AI tools to deliver that improvement is absolute possibility. And that takes away the strain and effort from the real network administrators and engineers who would typically have to look after that. So what you're seeing here is a very good use of AI technologies to deliver assistance. So whether you call them co-pilots or assistants, but basically some support for you in your work you're doing. And it's kind of been there for a while already. People focusing on Chat GPT and these sorts of things. But if anybody who, a good example is here on this screen, right? So the new AI laptops that are coming out, which I think are using the Meteor Lake processor from Intel, they're able to deal with this. I've got a background and a green screen on me at the moment, and typically on a predecessing piece of desktop technology, that to do that, to blur that out, to apply that inference and pick me out of the picture from all the stuff that's going on behind me, would take sort of 20% of the CPU power. You move to, with the accelerator, the coprocessor now in place in the new chips that are in the new platforms, that's reduced down to 1%, allowing your computer to do more of the things that you want it to do, whilst at the same time applying those proper filters and backgrounds and that support that you need in sitting in a seminar and having a nice backdrop. So those things are always there, and they've been there for a while. I mean, even with phone apps, if I look at phone apps and it sort of says, okay, I want a picture in the style of Monet, or I want to put my photograph in the style of whoever. That's AI. It's saying, okay, I've learned this style. I have a filter. I put it onto your phone, and it's been, as I say, it's been there for a while. I remember being very impressed. I went to the WebW3C conference in Lisbon many years ago. My taxi driver only spoke Portuguese. Me and my colleague only spoke English. He wanted to drop off somewhere which he hadn't requested. He spoke to his Android app in Portuguese. It translated it back pretty well, actually, in English. And that was 4 or 5 years ago. So that's natural language processing that is and can only get better. But it's good. I mean, these are the way that they're assisting us, and they will continue to assist us, and it will improve on them as it goes forward. But it's not a silver bullet, and it does require really good engineering to bring that solution from the potential within the semiconductor itself through to the application that you and I are going to use. At the other end of the story, we are in we're in a real hype cycle. In fact, I haven't really seen anything. Maybe blockchain was it, but for me, a little bit redolent of the .com boom bust thing at the minute, where AI can do anything. Back in the .com days, all you needed was a PC and the ability to code up some HTML, and you were going to be the next, the next retail superstore sort of thing. So there's a few products coming out. Again, this is a YouTube video posted by a guy called Dave 2T, and he's looking at 2 products. These are little hardware products. One's called Rabbit R1, and the other one's called Humane AI.pin. The Rabbit R1 is selling for $200. the human AI pin sells for $700 with a subscription. But the Rabbit R1 has got this 100,000 pre-orders at the moment before it goes on sale, and it's going to be released soon. And they work in the normal way, you know. They're pieces of hardware. They respond to voice commands, but there's a lot of hype on around it. So, for example, as Dave mentions this, he talks about, you know, it being able to, you issue a few commands saying, find me a holiday in Portugal for the family, because I want to go and have a lovely summer in the Algarve, and it taking all that action and delivering that booked holiday for you with flights, insurance, etc., etc. That's just not realistic. It's not going to happen. And to the extent that it can happen, it will happen. You know, your phone technology is that edge device that's doing most of that, and it's got a lot of precautionary stuff built into it. You know, the protection around the use of Google Pay or Apple Pay is significant. And so these for me are examples of people jumping on a bandwagon and trying to promote things which aren't going to really assist you and actually will cause damage to the actual usage, the positive use of AI as we go forward. I'm much more interested in the small things that it can do, the small ways it can help people realistically in their day-to-day work. Which are many, and I've been through a couple of them here. So they're the things, you know, it's going to help with information overload, but it's not a silver bullet, and it's not going to solve all your headaches about booking a family holiday for sure. So any comments on some of that?
Yeah, I'd say I think technology is at its best where it reduces friction in small ways, and I think solutions that just incrementally improve the way a particular system works often tend to be successful. You know, I think just competently delivering what people want is often a game changer.
No, I agree. Yeah, I agree. Not trying to blow people's socks off with something wild and super imagined. You're right, just competently delivering what people actually do in their day-to-day lives. You know, and when you're working on where the market's going, you should be thinking about that. I worked with a professor, one guy in marketing, and he said, well, the thing about marketing is actually it's already there around you. You already know it's going to happen. You should know what's going to happen next, because self-service was obviously going to happen in the supermarket. For me, Apple was obviously going to be a success once it transitioned to the Intel chip. Frankly, it wasn't anything to do with the mobile phone, and the reason for that was because I come from a software engineering background, and I knew that kind of opened all sorts of doors for them, and all of a sudden made them a safe company to work with. You can see that, and so you can see, you know, if you understand the milieu in which you sit, you can easily see the directions of the way it's going. I mean, it was obvious that social media was going to be the next thing. You know, I wish I'd kind of been one of the first mover people to take advantage of it, but it was obvious that it's going to be the next thing. You could easily interact and with other people around you. You could easily produce what it is that you wanted to talk about. And now, you know, a lot of these tools, when people are out there producing videos, etc., a lot of these tools, these AI assistance tools, are helping them do that competently better, as Marsh just put it. And so that's why the technology is coming forward, and that's why it's going to remain coming forward.
Yeah, it's this kind of like a resource multiplier, isn't it? So
yeah,
you know, creatives can generate images according to their specification and their imagination much quicker using AI-enabled tools.
Yeah, resource multiplier, but not a Marvel comic superhero, which is
yeah. Should we move on to the next slide?
Yeah.
Yeah, cool. Yeah, so I'm just going to cover 3 interconnected topics. So first is the deployment from cloud to edge, the details of it, how it's done, what are benefits. There are basically 3 pillars, and the second pillar is the heterogeneous computing and bringing the benefits of it to the edge. And the third is software-defined vehicles. So none of these terms is really new, but their current surge in momentum make them relevant to discuss it today. So let's start with deployment from cloud to edge. So the edge can refer to two terms. First is that the edge is the part of the cloud outside of the data center facility, and the other one is that the edge is just an IoT device, usually embedded system, connected to the cloud. And we're going to cover the last, but with a bit, there's one difference. So basically, what we can see that we already have edge IoT devices connected to the cloud. This is a thing we get hundreds of such devices deployed. But the difference is in approach of the industry of developing software for the edge. So as an example could be the SOFI SDV. When we develop in cloud a native application that are containerized, and then we can easily deploy it to the edge. And what's more interesting is that the architecture, so the native code is compiled for example, in this case, for ARM. So the ARM is running on in the cloud, and then using orchestration tools, we can just easily deploy it to the edge. And that really changes the way we develop software. Yeah, so we are trying to transition to develop the edge native in the cloud, and then easily switch to the edge. The use case there can be a few use cases. One of them is that we are doing a development for a platform that's not yet ready for deployment. It doesn't exist yet. It's not available to us. So we are doing with some kind of abstraction, developing in the cloud, and then we are deploying it on the edge. When we add a few more things to this stack, like continuous integration, continuous deployment, and microservices. When we try to write our software in microservices, then the edge and the cloud seems to be the border between them seems to be transparent. So we can switch a service to be running on the edge and on the cloud, depending on our needs. And moreover, when we do software development in microservice architecture, we can add more power to the edge device pretty easily. So imagine that you want to buy a car, and there are a few options, from the cheapest to the more expensive. Of course, the more expensive options, it's more expensive, and it requires more computational power. And what a manufacturer can do that in that case. So we create a cluster of edge. So we are just adding an extra unit or 2 extra units to increase the computation power of the edge. And the next topics will be heterogeneous computing. So currently, it's not a new technology. We got the 2 main technology of this is OpenCL and SQL. OpenCL is a bit older. SQL is more modern solutions. Both are maintained and partially developed by the Kronos Consortium. And also we got one API, which is maintained by just recently established UXL Foundation. It's Unified
Acceleration Foundation, yeah.
Foundation. So one API is based upon SQL, but it adds ecosystem to it, libraries. So it's a really huge chunk of software. And one API is more to be used in data center in HPC. However, the SQL, the OpenCL, and other related technology, including one API, could enable us to use hardware acceleration, like GPU acceleration, on edge. Because this technology works like this. We just write a source code for some physics computation, math computation for AI. and then we can run it out on whatever hardware we want. So we want to it on embedded platform, it's okay. We want to run in a data center, it's also okay. But we can also use as the device that makes this computation. It can be GPU, it can be CPU, it can be any other hardware accelerator. So that's the main benefit of heterogeneous computing. And now comes the software-defined vehicle. So basically, with software-defined vehicle, there comes two main concepts. So in the old days, we thought about the cars, about the smartphones on wheels, because we thought, well, smartphones provide me so many features. I just want to have it in my car. And industry, for different reasons, partially failed to deliver that. But also, it turned out there are other requirements for a car. It's called not a smartphone on wheels, but habitat on wheels, because we want our car to watch what's happening inside the car. Like, we want our car to watch our kids at the back seat and detect any symptoms of motion sickness, so we can just pull over. And also not only inside of the car, but also the what's happening outside of the car. And for this, we need computational power, a lot of probably, because observing passengers, drivers require just a lot of computation. So here we'll probably or will just deploy the heterogeneous computing with all of its capabilities, especially in safety critical flavors like SQL, safety critical, or for example, Vulkan for displaying in safety criticals. The other thing that's connected to the first topic, it's cloud to edge deployment. So there is a digital twin concept. The concept is to have all of the all of your parameters of your car and states of its components to have in both locally on the edge in the car and in the cloud, because we want to have enabled developers to develop the solutions in the cloud and easily deploy it in the deploying on the car. So probably when you're trying to develop application that watches other passengers, you want to do this in the cloud outside of the physical car, and you're doing the development on the car, and then you're deploying it and open the whole platform for the developers. So just SDV stands for a fully programmable car. The pain point of this is how to make it secure. So all of these topics that Moz mentioned need to be also taken into consideration. And in case of SDV and deployment from cloud to edge, this is the biggest challenge. And currently the industry is working to make that happen, to have a open API, easily programmable to be the ability to develop in the cloud with DevOps methodology and deploying it on the edge, and at the same time meeting all the security standards and as well in all the security doubts and yeah, the problems that can arise from having sensitive data on your edge. Yeah. So for now, that's all from my side. If you get any questions, I'm happy to answer them.
No, that's good. So let me understand a little bit more about the OpenCL and SQL. They kind of provide these levels of abstraction that you've spoken about. But how does it actually, when it targets the end user piece of semiconductor or system on chip, that's done through a process of an intermediate representative language? Is that right? So the way that there's lots of steps.
There's a lot of steps, and the basically every GPU vendors or hardware accelerator vendor, it's done a bit differently. some solutions use more open, let's say intermediate steps. Some are more closed, like we discussed on the ecosystem and on the first slide. So it really depends. There are open APIs, but they are not always the case for all of the vendors.
Interesting. And with the car, if it's a safety thing, then that's not where we're going to be relying on a LLM, right? So I mean, and the reason I say that is because, again, I was at a conference at Institute of Engineering and Technology, pioneering change and innovation, next gen IA, and one of the key facts that came out of that is that anything that's probabilistic, these LLM models are producing accuracy to about 94%, which, when something needs to stop or start, then it needs to be 100%. So anyway, that's great.
Yeah, so basically that's why SDV tries to answer. So they try to isolate the non-critical code from critical code. So even if a model makes a bad decision, there are layers below that can answer, no, we won't do that. Yeah. Because there's no condition to open your trunk because you're driving at a highway. Yeah.
If we open the automotive can of worms, we'll be here all day. So I think we should move on.
There's a lot of stuff.
Okay, so do you want to talk about the first one, Oscar?
Yes.
Success stories.
So regarding the firmware development for cryptography and compression hardware accelerator, so we delivered this project for a major semiconductor manufacturer, and as Mobica, we covered the whole software stack. So basically, that was a dedicated device that offloaded computation from CPU and handled it mainly for cryptography and compression. So let's say we have a data center, and we are serving websites, and there is a lot of cryptography nowadays because every connection is secure, or at least should be secured. So it's not cheap to make this computation CPU. We want to upload it to a dedicated hardware, to an accelerator. And we did development of firmware just running on this hardware, the driver mainly for Linux and other POSIX operating systems, as it was for the data center. So here Linux and POSIX systems just are our leading solutions. And also we did drivers in kernel space and user space, because the more you have the driver written in user space, the better and then more reliable solution. And we did a really comprehensive testing application that tested user API and also hidden debugging API that we could sometimes reach out to hardware internals not available for end user. Yeah. And we're working on a few generations of this product and still working on this.
Cool. The second project on this slide is a project that was from a suite or a program of different projects that we did with this particular organization, and they were looking at integrating sensors into everyday objects and using those sensors to interpret natural movement. So whether that's swiping on an item of clothing or making gestures with your hand in front of a radar sensor. Our contribution to this project or these projects was one, to integrate the sensors into those devices, so the bread and butter embedded development part of that, but also the interpretation of the information coming from those sensors, using machine learning models and algorithms to interpret, those numbers into inferences as to what people meant by making those gestures. So that was a really cool project that we had a decent number of engineers working on in partnership with the organization. The third project is one that Mobica has particular skills in, and that's GPU driver implementations. And so this one project was in an automotive context. So as Oscar mentioned, processors are getting more and more powerful in cars, but there's also a drive to consolidate processing into fewer chips on cars. And one way to do that is to provide virtualization. And what this project it delivered was a driver to enable a single GPU to be shared between multiple systems. So in this case, there was an infotainment system and a secure system, and the GPU could be time sliced to be shared between those two domains in order to keep, whatever's playing on your radio, or if Spotify were to crash on your system, it wouldn't bring down the speedo, and you'd still be able to control your car. So we implemented a kernel driver to support that GPU sharing in safety critical and non-critical domains. Another good project that we worked on.
Yeah, it's worth adding, although we're not going to reveal the names of our customers' clients here, is that they are all blue chip companies, Fortune 250 companies, and the technology is significant and is used significantly in the environment in which you work today. So live and play today.
So we'll crack on. I think this is your slide, is it, Robert?
Yeah, there's a couple of slides here at the end, really just to give a little bit more of an explanation about what it is Mobica Cognizant do. And this one splits us out in the areas that we work in. So we've got this strong degree in verification and validation. So when you're developing a product, if you're working at the chip level, you need to validate that the requirements are there's no duplication requirements, the requirements are complementary, that they could be engineered incorrectly. And once you've got those valid requirements, then you need to test them as you implement that semiconductor, and you go post tape out, you've got the semiconductor available, and verify that those requirements have actually been met. So first of all, did you get them right? Then secondly, does it do it? And that's an area that we've done an awful lot of work in. We do a lot of work at the system software level. So Moz and Oscar there were just talking about work that we've done on GPUs and drivers in general. Drivers are things that attach the operating system to these ancillary devices that exist within a solution. And there are other systems pieces of software. So there's the tools that help developers use that semiconductor effectively. So they're plugins and pieces of technology such as mathematics, algorithms, etc., that are implemented for you to use effectively. Then there's the middleware area where we work in. So this is one that allows us to provide integration, the glue layer, the middleware area, the integration for the total software stack from top to bottom. And then I guess there's really the application at the end of it. So wouldn't want you to walk away from the seminar thinking maybe Cognizant really are only focused on some things that are very low level, down at the hardware and firmware level. We do the whole stack. So if you were to walk up to a vending machine or look at an interface which is non-standard, such as in a car or in a boat, then we would be doing the HMI part of that. In fact, one of our clients makes a lot of home products for drying hair and vacuum cleaners and things like that. And the companion app, we worked with the hardware extraction levels to help them select the silicon, and then right through to the companion app, which is a generic name for the application that you get with every product you buy these days. So we do the whole stack. So this is a very generic picture of where Mobica works and the sorts of customers and clients that it takes on. You just want to move on to the next one more, and I'll just kind of recategorize them here. So down at the bottom level, that's where we work with our semiconductor clients as they go through the design of the processor, making sure that systems, those systems libraries, that firmware, in areas such as encryption, but also in things like network drivers, etc., are available, allowing our client to press on with designing a sophisticated piece of silicon whilst we make sure that the firmware and software that sits above that works effectively. And then there's the process of manufacture packaging. So that's working with the platform. And really what I'm talking about here is helping people who are building products that help in the production of semiconductor. Companies like SML, for example, they're the sorts of people that we can provide solutions to. And then there's a software ecosystem, very important area. This is the one whereby you'll know packages and products are out there, such as TensorFlow and PyTorch and things like that, but they kind of work at a high level. To get them to work really effectively on all these different heterogeneous hardware semiconductor areas, employing a company like Mobica Cognizant is a company that could help you do that, to make that framework take maximum advantage of the hardware accelerators that are available to it. And then finally, the smart product one's the most easy to understand, if you like, which is, as I say, it's your hairdryer, it's your in-home device. They are the products, your white goods, your intelligent microwave, etc., etc. These are the products whereby we help you embed and again maximize, make sure that you're using the appropriate semiconductor and get it integrated properly into the full solution, from the human machine interface down to actually controlling the device itself. So that's a quick run through the sorts of the areas in which Mobica Cognizant can support you and do support our current customers. And we just use that to sort of draw an end to this seminar. So
yeah, I think the next slide is gives us a nice segue into the Q&A session.
Yeah, and so I'm going to leave you with Oscar and Moz now. There's something else that I need to go to. So I'm going to leave you with Oscar and Moz as we go into the Q&A sessions. Please ask them questions, as I'm not going to be there to answer them. Ask them really difficult questions, and we'll see what comes out of it.
Okay, then. So thanks to Rob. So we're just waiting to see if there's any questions that come through from, how many people have you got listening?
You're happy to answer them.
Yeah, 47 people. So hopefully somebody will ask us something. Otherwise, it'll be a short. Oh, here we go. Here's a question that's come through.
Okay, so how will semiconductor firms and AI tech providers collaborate or face challenges in the future?
Do you want to handle this one?
Yeah, so my bet is that we will perceive current AI models and large language models as we today perceive video games from 90s. I mean, there are many great ideas in these games that are visible in gaming today. However, from perspective of time, they are pretty immature. And yeah, that's the same for AI, I think. So probably we are going to have a few breakthroughs in AI technology. And the quite important thing that was mentioned internally by some leading company, that there is no mode. I mean, no mode is that the current AI leaders know that others as competitive models can be created by startups or by open source models. It hasn't happened yet, but they're aware. I mean, just they aware of it as a risk for them. So what I want to say is that probably things gonna change. We don't know yet what will be that, but we can, let's say, try to maybe not foresee future, but try to deduce it. So I would expect specialization in AI semiconductors. For example, if the transformers architecture for AI will win, then probably we can expect the hardware that is just specialized in transformers architecture. Yeah, that's one thing. The other that we can expect, I think, is running. Currently we see a huge demand for heavy duty GPUs for data centers. And the demand for it is so huge that currently I see a niche, and we see some companies already doing that. Hardware specialized in inferencing network. So we just run network on this hardware, not train it on it. So that's the second thing. And the third thing is that the also related with inferencing. So probably we're going to see much more devices, IoT devices like sensors running AI networks, inferencing them. And for this, the power efficiency, power management will be key. So we would like to have a device with a battery running as long as possible. So yeah, basically there are just a few things I would consider regarding the how the development of AI and semiconductors might come along in the future. Yeah.
Just to add to that, I think from the collaboration side of things, you get like industry consortiums or organizations that come up and companies that otherwise are competing against each other work together to build like a platform to allow other people. I mean, like you see it with graphics. So Kronos Group arose out of just fragmentation of the market and the industry coming together and saying, look, we need to define a standard so that our customers can all build on the same API and we can compete on a performance basis towards that API. And so in the AI space, you've got CUDA, which is some would say in a monopoly position, and then you get various initiatives by other companies collaborating to try to break that. So you've got UXL Foundation, which we've also mentioned on the call earlier, and so that we don't know whether that'll be a successful attempt, but it looks like it's a promising initiative that might have legs.
Yeah, at least we will have standardized APIs.
Yeah. Cool. Security, AI, and accelerated computing are increasingly integrated into everyday tech products. What does this mean for semiconductor companies' product development and innovation? So I'll take this one. I'd say that there's a few different aspects to this, and so you've got AI acceleration. Obviously, there's a push to get edge devices on devices on the network edge to do more of the AI lifting rather than sending voice, video, whatever the sensor input is on that edge device back to the data center. And so the response to that will be greater AI processing on smaller and smaller chips. So you've got things like TinyML. You've got perhaps bigger frameworks. Llama, a large language model that can be compressed and run on smaller devices. But there has to be like an equilibrium point where the devices meet the processing requirements for the application. So you'll get expansion of AI capabilities in the silicon to facilitate greater intelligence at the edge. Security will demand the features that we mentioned, and so you'll see silicon vendors offering more of those secure elements in their smaller microcontroller offerings, as well as the application processors as well. Yeah, and I guess having those facilities on those smaller and smaller platforms will provide the fertile ground for new innovations as well. So obviously, there's applications that we can think of that benefit from that. You know, voice assistants, cameras, and object detection and things like that. But by providing those basic building blocks, you provide the fertile ground for people to innovate as well.
Yeah, what I am really curious about is about the RISC-V adaptation in the AI related embedded system. Yeah, it's a pretty new player here, so we'll see how much attention it will gain.
And we've got a question. How can semiconductor companies leverage embedded systems expertise to design and integrate Gen AI capabilities into a diverse range of devices and applications? So I'd say that one of an example of say Gen AI capabilities. We worked with a partner silicon vendor to facilitate one of their demos at CES this year, and I think it's going to be part of the demoware over the next few quarters. And that's the integration of a large language model in a car context. And there's a two-tier system that operates in that demo that we worked on. So there's a local LLM integrated onto the silicon, accelerated by the NPU that's on the device, and that provides quick, immediate responses, low latency responses to queries coming from the customer. So there's voice input. You ask the device, what's your hotel options, while you're on the road, and the LLM is able to interpret that, understand the context, understand where you're going, but it doesn't have that real-time information, so it reaches out to the internet to pull in the data from a booking website or whatever, and so there's a few elements in play there. There's connectivity elements. There's local processing. There's also a cloud fallback as well if the local LLM isn't able to answer it appropriately, and so there's like a multi-tiered response to the kind of applications that people will expect by that use Gen AI, and I think being able to facilitate like that kind of seamless switching between local and cloud processing is probably an interesting space that silicon vendors can probably facilitate using not just their devices, but also the software stacks that they provide on top.
Yeah, also from a bit different angle, if I were a semiconductor company, I would think it through about the drivers and interfaces I would like to support on different set of platforms, because that's the way of the best incentives for users to use your platform, because you have interfaces that their software is supporting. So in this case, just off the top of my head, I would think about the supporting like interfaces like SPURV and some of the Vulkan computations, OpenCL interfaces. So when you support SPIR-V, when you support Vulkan computing, for example, then a really broad, I mean, just a high number of heterogeneous computing system can leverage your hardware. So that's quite important. So like your users are going probably using heterogeneous software, and what they expect is to easily deploy it on your platform, so you can appear and say, hey, it's easy to use our platforms because we have driver, we follow, we have implemented some standards, and therefore whatever software you use, you will be able to utilize our semiconductor.
Yeah, I think that trend of Vulkan being like the common compute platform across everywhere is really interesting. Could potentially, well, it opens up a really rich ecosystem of tools and capabilities, really.
Yep. So maybe it's time to just round it up. Maybe it's a good follow up. So if you have any questions still, but they will come up. You will come up with this question after this webinar. Then you can just reach us on LinkedIn.
Yeah. It's been a really interesting chat. Hopefully you guys enjoyed it, and follow that QR code to connect to us on LinkedIn. If you've got any follow-up questions, feel free to reach out to us via LinkedIn. And thanks for listening and watching.
Yeah, thank you.